Hello, everyone. I think we can get started right now. Yep. Well, hello, everyone, and welcome to the fourth session of the ISRM Young Members Seminar Series. My name is Moji Mohammed Nejad, and I, as part of the ISRM Young Members Group, I'm happy to chair this fourth monthly seminar. It is a great pleasure for us to be here today, and we would like to thank you for attending this fourth session. Before starting, we would like to thank the support from the International Society for Rock Mechanics and Rock Engineering, and especially to Sevda Dehhoda, ISRM Vice Presidents for Australia and Chair of the ISRM Young Members Committee. We also would like to thank you to all young members, representatives of national groups that have joined this initiative from all around the world. Finally, we would like to thank Dr. Salaheddin Akhtak and Ms. Corinne Singasin for agreeing to present their work in this session. Before our speakers begin, we will take a moment to present key information about the seminar series. This project attempts to promote the community interested in rock mechanics, including engineers, research scientists, and students, to foster knowledge in rock mechanics among this community, to share experience both in the industry and academia, and to strengthen relations between different countries. We would like to invite a variety of young members to participate in this seminar series. The criteria for the speakers are as follows. First, be an ISRM member. The second one, have maximum age of 35 years or of 40 years if a PhD degree was obtained in the previous 5 years. And last one, have worked in rock mechanics and rock engineering for a period no longer than 10 years. Speaker nominations can be made by nominees' national group or by some other person or organization acquainted with the nominee's work. Self-nomination are also accepted. Nominations are to be addressed to the ISRM Young Members Seminar Series Organizing Committee. On the screen, you can see our contact email. This webinar will be held every month. We invite you all to keep in touch. We will now begin the first seminar of the day. Each presentation will last 20 minutes and will be followed by 10 minutes of question and answer. For the smooth running of the seminar, please turn off your camera and microphone during the presentation. If you have any question, you can use chat and also raise hand feature. Okay, let's move on to first speaker. The first speaker is Dr. Salaheddin Akhtak, who is a postdoctoral research associate at the University of Adelaide. He obtained his PhD in 2019 from the University of Adelaide, investigating the mechanism of strain bursts in deep mines under Coop influence of elevated temperature and high confinement. After completing his PhD, he continued his work on strain bursts, focusing on in situ stress measurement methods and stress memory effects in rocks. His current project is related to an innovative cold burst system to investigate the influence of confinement loss and preconditioning on cold burst mechanism. Today, he will be presenting a talk entitled Experimental Analysis of Burst Type Extreme Rock Failures and Rock Fracture under High Stress Conditions. Dr. Akhtar, the floor is yours.
Thank you, Moji, for the introduction. Let me share my screen first. Can you see my screen now?
Yes.
Okay, I'll start my presentation then. Thank you again, Moji, for the introduction, and thanks to ISRM and Sevda for the opportunity, and the ISRM Young Members Board as well. So the title of my presentation today is Experimental Analysis of Burst Type Extreme Rock Failures under high stress conditions and rock fracture under high stress conditions. And this research has been supervised by Associate Professors Murad Karakush and Jiang Miang and Abbas Tahiri. And as Moji said, I'm Salatin Akhtar. And this is the outline of my presentation. So I'll start with a brief introduction to the deep mining and rock burst, and this will be followed by the experimental analysis for rock burst investigation and the energy concept. I'll briefly mention about the energy concept of bursting mechanism, and after this, quasi-static and dynamic fracturing mechanism during bursting will be mentioned, and I will finalize the presentation with the concluding remarks. Oh, yeah. First, I would love to give you a brief introduction to the need for deep mining. As we all know, the resource consumption is increasing rapidly due to the growth of the global population and the new products and markets. This has caused the global demand for minerals to increase exponentially, leading to decline of ore grades, and consequently, consequently mining volumes are progressively increased, and underground mining continues to progress deeper to greater depths to sustain the supply for the growing demand. And rock burst, which can be considered the cancer of deep rock engineering, and can be defined as a large volume of ejected rock fragments caused by the instantaneous release of accumulated excess strain energy from highly stressed surrounding rocks in deep underground or highly buried excavations. So this phenomenon causes significant risk in underground operations and could potentially lead to personal casualties and equipment damage, and that could also lead to some delay in the excavation operations. It could also trigger some microseismic events of magnitude more than 2 on the Richter scale. So it's been one of the most serious and yet least understood problems in deep mining and tunneling operations. Rock bursts have been occurring worldwide, and they've been in the past decade. They've been recorded. Numerous rock burst events have been recorded worldwide. So here's an example from WA in Australia. And in 1999, in one of the gold mines in WA, a rock burst occurred, and 40 cubic meters of rock had fallen during that incident, and quite a large microseismic event happened as well. Another example from Canada in 2009, and from a copper and zinc mine in Ontario, another seismic event got triggered by the rock burst, and more than 2,500 tons of material was displaced. And another example from a coal mine in China, and a huge amount of energy released during the burst, and unfortunately 5 casualties happened by the end of this accident. So just to visualize how a rock burst occurs in underground or highly stressed mining excavations or highly buried tunnels. I would like to just show you two videos of short videos of rock bursts. It might be quite loud. Like, as you can see from a working phase, the rock fragments ejected from the working phase instantaneously at a certain speed, which, to be honest, like looks quite scary. And another example from a working phase in a tunnel, in an underground tunnel, the workers were not aware of that was going to happen, and it ended up lifting a very heavy vehicle in the underground tunnel, and luckily no casualties happened in that one. And so it's really, rock bursts are quite dangerous dynamic incidents, and the ejection velocity of the fragments from the free phase, from the working phase or sidewalls, could go up to 20 meters per second. So the underlying mechanism of it should be understood very well. So far, lots of studies have been carried out in the physical simulation of rock bursts in the laboratories by replicating the phenomenon under uniaxial and triaxial loading or unloading conditions, and a substantial understanding of rock burst behavior has been gained through these studies, as well as the field observations as well. However, there are still some outstanding issues that needs to be addressed and clarified in the mechanics of rock bursts. So the excavation of the deep high stress rock masses will inevitably causes an unloading affecting the mechanical properties and the energy storage characteristics of the rock. So therefore, the excavation unloading is an essential factor to study in rock bursts in deep underground engineering. For this, some big, expensive true-triaxial rock burst testing frames have been developed in the last decade, replicating the stress paths in an underground excavation by introducing a sudden release of the minimum principal stress, mimicking a free phase or an excavation in underground. In order to better understand and determine the excess strain energy characteristics, which can be defined as the potential energy for rock burst, here in Adelaide, we have conducted some lateral strain control, a series of lateral strain control, uniaxial and triaxial compression tests, and the snapback behavior of the thermally treated granite samples have been obtained by these tests. And according to the results, a delay in the bursting was observed at higher temperatures, and the samples also tended to burst in a more intense manner as a result of the thermally induced microfractures. Confinement, it's also been observed that confinement has a significant influence on the post-peak energy characteristics. So more severe bursting was observed with increasing confining pressures. So for rock burst, a prerequisite for rock burst is that the excess strain energy exists to eject the material fragments from after the failure. So when the elastic strain energy in the rock exceeds the capacity of the rock storage capacity, certain amount of energy mainly dissipates by rock fracturing, and the remaining part of energy mainly used for as a kinetic energy of the rock fragments during bursting. So in other words, the rock fracture may not be able to dissipate the entire potential strain energy, and a portion of it is transferred into kinetic energy to eject the rock fragments which lead to the occurrence of rock burst. So we have done some energy analysis after those tests and determine the excess strain energies. So the excess strain energy is important because in order to eliminate the rock ejection in underground, it is really required that the energy absorption of the dynamic support system used in the tunnels or mining excavations must be greater than the excess strain energy of the rock. So that means the more the energy dissipated by the rock fracture, the less energy the support system needs to dissipate during any dynamic event, any dynamic rock failure. On the other hand, in the last decade, there are a few big true-triaxial loading frames have been developed. This is an example of them at the State Key Laboratory in Beijing, China. So this work was conducted in 2018, and we used the true-triaxial loading bursting testing system there to do some rock burst tests on using granite. And this testing system is composed of stress displacement acquisition system, and here's the main loading machine and the hydraulic load controlling units, and also acoustic emission monitoring system is used during the tests, and high-speed camera is also used for capturing the ejection of the fragments from the free face of the rectangular samples to determine the kinetic energies. And here's the loading plates in three principal stress directions. To illustrate how the test is happening in such a big frame, in such a big testing frame, a rectangular sample is loaded independently in three principal stress directions up to the predetermined stress level, which is the institute stress level. When that institute stress level is reached, the loading pattern in the minor principal stress direction is dropped, creating the free surface on the rectangular sample, and while keeping the intermediate principal stress constant and increasing the major principal stress until bursting occurs. And these tests, we conducted these tests with a collaboration of Professor Hilman Shah, who is a very well-known rock burst expert in the rock mechanics area. Actually, here's an example of the ejecting fragments from the free face of the of a rectangular sample. As you can see, it started with small grains ejection from the free face with the increasing axial load, and it failed after a certain after the capacity exceeded. And using this testing frame, we have studied the thermal damage influence on bursting mechanism under true-triaxial loading, unloading conditions, and based on the stress level and the kinetic energy calculated via the high-speed cameras and the acoustic emission responses and their characteristics, the damage state of bursting was identified both qualitatively and quantitatively. So, this is an example of capturing the injecting fragments from the free face. In this study, some bursting indicators have been also proposed to evaluate the degradation of the rock and the bursting processes, and the bursting severity was quantified by the kinetic energy of the ejected rock fragments. And as an alternative to these big expensive testing frames, here in Adelaide, we have proposed a burst testing methodology using hollow cylinder samples. In this methodology, we could also mimic the stress states in an underground excavation, and by applying internal confinement, external confinement, and the axial loading, which enables us to replicate the three principal stress states. In order to verify this, we used acoustic emission responses during these true-triaxial testing using hollow cylinders as well. We tracked the deformation and the bursting processes during the tests. And in order to verify the acoustic emission responses, we implemented a boroscope to verify the results during the tests. Here's an example of one test that was done recently. As you can see, we have the acoustic emission responses on top left here, and the load displacement behavior on top right here, and the boroscope image, the video of the from the inside of the hollow sample is shown here. And let me just play it again. And bursting, we can observe the bursting during the test, and they relate the acoustic emission response, and they follow up the force displacement response at the same time instantaneously as well. Here's an example of another example from an underground tunnel, and on the right-hand side are showing the examples of bursting in hollow coal sample, bluestone, and granite. And a bursting happened here, and just now granite is burst, and we can observe the crack generation and propagation in the hollow samples and the bursting at the same time to show that this bursting phenomena could be replicated in the laboratory as well. As an example of bursting in bluestone, as you can see here, we have obtained the stress strain behavior and also the acoustic emission responses to detect the any kind of deformation and the evolution of the failure and bursting. The evolution of rock burst showed a local grain ejection from the sidewalls of the hollow cylinder, and it was followed up by the fragment exfoliation, accompanied by some crack generation and propagation, and eventually bursting occurred when we increased the major principal stress level. So in order to quantify the damage, we have also conducted some micro CT scanning before and after each bursting test to provide a non-destructive 3D imaging of the fracture evolution of fracture network during bursting. So a stack of 2D X-ray images was reconstructed to produce a realistic 3D virtual volume of the each voxel that represents the X-ray absorption at that point. So this has also enabled us to measure the crack density and the fracture surface area happened during the burst, generated during the bursting, and the volume of the fractures within the rock. So this is another example to show the vertical cross sections which also enabled us to detect the locations of the bursting pits and the fracturing evolution. And using the 2D stacks of images, we have reconstructed the 3D networks of the fractures during the bursting tests. And we have also studied the influence of confinement level on bursting. So in this case, as you can see here, a hook cell is used for the external confinement, and And water pressure is applied as an internal confinement by using a syringe pump and MTS compression machine used for the axial loading to apply the true-triaxial loading and unloading conditions. In the meantime, during tests, we monitored the failure process using acoustic emission and force displacement behaviors. And based on that, we have, as you can see, we lost the confinement. We just removed the internal pressure from the hollow cylinder by using the syringe pump. So we replicated an excavation in the laboratory by releasing the internal pressure in a hollow cylinder. And here's an example of the bursting pits on a hollow sample. And then we did the micro CT scanning to determine the fracture surface area of these samples generated during bursting. And because we know the fracture energy of the sample, by using the fracture area generated, we can calculate dissipated energy during fracture by generating new fractures and also expanding the pre-existing fractures during bursting. And we can also determine the kinetic energy dissipated rather than the fracturing mechanism rather than fracturing during bursting, which is directly related to the bursting severity. We've also done to understand because the initiation of bursting is a quasi-static fracturing. We've also investigated the underlying fracturing mechanism of bursting by doing some fracture toughness tests under various strain rates and also temperature levels. And because we've also investigated the dynamic fracturing characteristics of bursting as it evolves as a dynamic fracturing phenomenon, and the effects of thermal damage and the impact loads on the dynamic fracturing and energy characteristics have been determined by conducting these dynamic fracture tests using a split Hopkinson pressure bar at the Monash University with a collaboration of Jian Zhao, who is a very well-known expert in dynamic fracturing. And with the help of a high-speed camera and DIC technique, virtual extensometers were designed, and displacement as well as the strength fields have been obtained, and also crack propagation velocities were estimated by using these, which are also used for dynamic fracture energy calculations. So the dynamic energy evolution characteristics have been determined and used to evaluate the bursting severity of granite on the different impact loads. And the bursting severity was determined based on the speed of the flying fragments during the testing. So it's really important to understand the behavior of the rock in the laboratory, and so we can relate that behavior and try to estimate how it would respond in the field. So by determining the excess energies and the kinetic energy levels, they can be used they can be used for the designs of dynamic rock supporting in underground to eliminate the risk of bursting. To summarize, in the laboratory, by conducting uniaxial and triaxial testing, we can determine the excess strain energy, which is the potential for bursting, can be determined, as well as the mechanical properties. And conducting some true-triaxial testing, we can determine the energy storage levels, kinetic energy levels, and also bursting stress levels based on the three principal stress levels. And the burst prone depth could also be estimated based on the results of that kind of testing. And we can obtain some insight on the quasi-static and dynamic fracturing by conducting fracture toughness tests, and as well as the ejection velocity and the propagation velocity of the fracturing during these tests. So at the end of it, apart from mechanical property, apart from obtaining mechanical properties, fracture parameters and energy levels, and also the stress conditions for bursting, by the end of it, we can determine whether the rock is going to burst or not. And based on that, we can also estimate the propensity or severity of the bursting. And in order to validate and verify the results, with an advanced true-triaxial loading, unloading conditions, we can mimic the bursting in the laboratory and visualize the fracturing in 3D to better understand the behavior in the field. So this is pretty much the end of my presentation. I would like to acknowledge our research team and the sponsors for this research. Thank you very much for your attention and your time. I would love to answer your questions if you got any. Thank you.
Thank you very much, Dr. Akhtar, for your very interesting presentation. I enjoyed all of the slides one by one. So now we have 10 minutes for the questions and answer session. If anyone has a question, just come in and ask question from Dr. Akhtar. Yes, please, Abdul Naji, you can ask your question.
Yes, I am Abdul Muntakim Naji from Pakistan. And first of all, Salatin, it was a very nice presentation from your side. And you have explained the experimental work very well. And I have a few questions. One is that from this all experimental work, what do you think, what type of constitutive model that rock burst follow? Because when we talk about conventional Hook and Brown or Moore Coulomb constitutive models, they are totally irrelevant when we talk question strain burst or first slip rock bursting. So what is your comment related to the constitutive model? And the second question from my side is that when we talk about stresses and fractures in underground environment, normally the fractures cause stress concentration. And due to this stress concentration, because these type of fractures act as a stress barrier. And have you worked on or the thought about this dimension that?
Oh, okay. For the second question, I couldn't quite hear what you said, what you were asking. Could you please repeat that again? Yes. For the stress concentration?
Actually, I have worked on rock bursting and numerical simulation, and I have simulated a rock burst for underground tunnel that was constructed for a hydropower project in Pakistan. And when I modeled the tunnel, I saw that the stress was specifically concentrated near a shear zone. When you have performed any experimental work, you have thought about that the microfractures which are present in the small size sample, it is very difficult, I think. But have you think about that it can be possible that those small fractures can be act as a stress barrier to concentrate the more stresses when the deviatoric stresses are very high. So I think you got my point.
Yeah, thank you. Yeah, thank you for the great questions, Abdul. For the first question, to be honest, in terms of the constitutive modeling, I would personally, I would recommend to conduct use plastic damage based modeling, because as you said, more column or Hook-Brown or Drager-Prager failure criterions are not quite enough to be able to use for bursting behavior. So plasticity damage based models would be more appropriate to simulate the bursting, to be honest. So you can, after developing the plasticity damage model, you can verify your results, your behavior based on the triaxial testing results, to be in here, based on your triaxial test, uniaxial and triaxial testing results. And after that, you can try to simulate the bursting occurrence, because there is not any standardized failure criterion for bursting just yet.
I think there are few. I think there are few, but I was curious that you have some point related to this or not.
In this presentation, it was just covering the investigation of the bursting experimentally, whereas in our research group, especially Dr. Rupesh Verma, he has been working in modeling side of the bursting, that he developed his own model during his studies. For the second question, yes, sometimes the stress concentration might trigger bursting easily. Rather than that, to be honest, some relief boreholes are driven in underground to reduce the impact of the bursting, rather than using that as a triggering mechanism. So we have to be really careful on that, because as you said, it might trigger or it might also reduce the impact of it as well. So with an optimum layout and appropriate number of stress relief boreholes or fracturing in the underground excavations could be used as a mitigation methodology. Actually, we are currently working on that, that I haven't presented in this presentation session today, but hopefully in the future, I would love to discuss the details.
Okay. Thank you, Salahuddin. Thank you.
Thank you, Abdul. Thank you.
Thank you, Salahuddin. Thank you, Abdul. Actually, Abdul, your question was related mainly to continuum damage mechanics and fracture mechanics when you were talking about the constitutive models. So this is from my own knowledge, and it's a bit interesting area as well. Is there any other questions to Salahuddin? No. Can I ask a question, Salahuddin?
Yeah, go for it, Moji.
It's just very simple question for you. How do you see rock base? Is it dynamic process or is it static or quasi-static? What's the nature of this?
It is a combination of both quasi-static and dynamic. Itself, it is a dynamic phenomena occurring in highly stressed surrounding rocks, but the initiation can be considered as the quasi-static fracturing. Yeah. But the evolution of it is definitely a dynamic unstable failure, dynamic unstable rock failure.
Yeah. It's quite, nice one, thank you. It's quite compatible with the fracture mechanics principle then.
Thank you.
Nice one. Is there any other question? If there is no other question,
I do have a question.
Yep.
Hello, this is Masood. I'm sorry that I raised my hand. I just have a question. Dr. Attat, very nice presentation. I just have a question with regards to the testing procedure that you explained. From my experience in the lab, the type of the class 1 type of failure we get is due to the type of controlling system that we use, whether method we use, whether it's a axial strain control, lateral strain control, and my experiences show that if we control the tests by lateral strain increment or rate, basically, we get class 1, and if we change it to if you control with class with axial strain, we get class 1. If we get it with control with lateral strain, we get class 2. And actually, there was a paper recently published by I think Professor Ming Kai, Professor Jiating Feng, and another gentleman, the first author, Dr. Hu, I believe. It was about post-peak stress strain curves, and they very nicely explained the mechanism there. So I was wondering what type of method you use for controlling these tests, whether there were axial strain or lateral strain rate control, and how do you find this influencing the results based on your experience if you tried with that? Thank you very much.
Yeah, thank you, Masood, for your great, interesting question. Yeah, as you said, like some researchers are using for axial strain or displacement or load control, or some others use the lateral strain control, as we did here in Adelaide. That was the main purpose was to, because we believe that the rock behavior, especially the brittle rock behavior, in the brittle rock behavior, the strain, axial strain does not increase at a certain behavior, because that was the reason why we wanted to use the lateral expansion as a controlling feedback for the axial load. So because it increases progressively, the lateral strain, the expansion is progressively. We believe that this is the real behavior of the rock that enables us to, in here, doing the snapback, that we can calculate the energy accumulated inside the rock sample, that in case of which is the potential of bursting that we propose here. And so this energy will be released in case of an release of confinement or any free phase that can be replicated in the laboratory. In their research, I haven't had a look at the details of them, but in our studies here in Adelaide, we have used mostly used lateral strain controls for uniaxial and triaxial testing. For uniaxial testing, the lateral strain was obtained by the chain extensometer, and for the triaxial testing, the feedback was feedback from the strain gauges mounted on the membrane, which is located inside the hook cell. That's how we control the loading.
Thank you very much. Very, very complete answer. Thank you. I really appreciate that. So, I was based on my experience, I saw that on the lateral side we get unloading as well. So when the lateral strain rate is high, the actuator moves back, so causing unloading. So what we see is not actually class 2, it's just unloading, and you see that on the lateral side, lateral strain graph as well. So the behavior of rock is something that is changing. In a sense is one thing, and it's not changing. It should not change with the way we treat the sample, based in the laboratory, based on the machine rigidity or the way that we control the test. It's just the way that it replicates or responses to the way that we test it. So on the lateral side, I see that we get unloading, and that unloading is elastic. It's not plastic deformation as we want to see, or damage into kind of deformation that we want to see. If we control it with axial strain, though, we usually tend to get a very sharp release of energy, and there's no kind of kickback in the axial strain kind of curve.
Mm-hmm. That was the actual reason, because in axial loading control, the brittle failure occurs instantaneously and it drops here, and that would not enable us to calculate the energy levels in the cosmic regime. So in this case, actually, we are just getting the feedback. So the rock itself is controlling this and releasing, as you can see here, in the next slide, that is more clearer. Here.
Sorry for interrupting. I think, we have just 10 minutes for question and answer.
Thank you
it's
so
very
much.
interesting just sitting here and here. You guys,
I would love to discuss that in detail, Masood, with you. If you can just contact me. Thank you very much.
We'd be glad to. Thank you very much.
As well. Keep us
awesome.
posted.
Thank you.
Well. Thank you, Masood. Thank you, Salahuddin. I will hand over to Jack then.
Thank you. I'll just stop sharing my screen. Yeah.
Right. Hello, everyone. So now, thank you all for the questions. I'd like to introduce the next speaker of this webinar session. So the next presenter is Corinne Singeisen, who is a PhD candidate at the University of Canterbury in Christchurch, New Zealand, researching earthquake-induced slope instabilities. Before starting her PhD in early 2020, Corinne obtained a Master of Science in Engineering Geology from ETH Zurich in 2017, and worked as an engineering geologist in Valais, Switzerland. Her research interests include geomorphology, landscape evolution, rock mechanics, and hazard and risk assessment of unstable rock slopes. Today, she will be sharing with us co-seismic rock slope failure mechanisms, insights from landslides triggered by the 2016 magnitude 7.8 Kaikoura earthquake. Ms. Singeisen, the screen is yours.
Thank you very much for the introduction. I'll just share my screen. Can you all see that? So today I'll be talking about co-seismic rock slope failure mechanisms from the 2016 Kaikoura earthquake. And the research I'll be presenting today is part of my PhD research that I'm doing at the University of Canterbury under the supervision of Chris Massey and Andrea Walter at GNS Science and Tim Stahl at the University of Canterbury, as well as in collaboration with numerous other researchers. So first, I'll give you a bit of an overview of the 2016 Kaikoura earthquake. Then I'll talk about co-seismic rock slope failure mechanisms. And then I'll talk a bit more in detail about some site-specific analysis of two co-seismic landslides that we did. And then talk about the conceptual models of failure mechanisms that we derived from this site-specific analysis, as well as in the end, talk about some implications for landslide susceptibility. So the 2016 Kaikoura earthquake was triggered in the northeastern South Island of New Zealand. And you can see the epicenter of the earthquake marked as a star in this map. And the earthquake then ruptured towards the north, triggering more than 20 surface faults that are indicated in red on this map here. And as a result of the earthquake, there were over 30,000 landslides triggered. And these landslides came in all sizes and shapes. So as you can see in some of these pictures, there's quite a variety of different failure types that occurred during the earthquake. And some of the main landslide failure mechanisms that we saw after the event were debris and rock avalanches, as well as rock slides. So why do we care about failure mechanisms? Well, there's an intrinsic link between failure mechanisms and initiation processes. So you can imagine that a debris avalanche doesn't quite initiate in the same way as a rock slide does. So that has implications for landslide susceptibility when we're interested in looking at which parts of the landscape are more susceptible to co-seismic failures than others. And also, failure mechanisms influence the potential hazard and risk that a landslide poses to infrastructure and also human life. So we're ultimately interested in learning more about failure mechanism in order to better mitigate the risk that earthquake-induced landslides pose to society. So if you have a look at the geological setting of the study area, you can see that a vast amount of the study area is composed of turles basement rocks. So that's this pink color in the map here. And that's a unit that's composed of primarily heavily deformed sandstone and some argillites. And this unit is overlain by late Cretaceous to Neogene sedimentary rocks, and there's also some quaternary sediments in the area. So I'll be talking about mainly two landslide sites today. So those are located in the south of the study area, and they're called the Mount Peter South landslide, as well as the Stanton River East landslide. So Mount Peter South is located in these turles basement rocks, and Stanton River East is located in Neogene siltstone. So to give you a bit of a better idea of what these rock masses look like, you can see a picture of turles basement rocks on the left-hand side here. So as I mentioned, those are mostly interbedded sandstones and argillites, and we usually group those together and call them greywacke here in New Zealand. So these rocks are heavily deformed, and they're characterized by really closely spaced discontinuities. So in this type of rock mass, we see discontinuities from the centimeter scale up to the meter and decameter scale. And regionally, after the earthquake, we saw that the main failure types in this type of rock were rockfalls, as well as debris and rock avalanches. On the other hand, in Neogene sedimentary rocks, which are typically massive but very weak rocks with an intact rock strength of lower than 2 megapascals, we mostly saw rock slides, slumps, and some shallow debris flows. If we then look at the literature, it's quite well known that rock slope failure mechanisms are closely linked to geology and rock mass quality. So in intact and massive rock masses, we do expect to see structurally controlled failures, as is shown in panel A in this figure here. If we get into more blocky rock masses, we then typically see more step path failures, so failures that are controlled partially by discontinuities, but can also include some breaking of intact rocks. Or if the rock mass is completely disintegrated, we could have circular failures as indicated in panel C here. So to understand the failure mechanisms in our study area a bit better, we conducted some site-specific analysis on a few selected landslides. So as an input, we used pre and post earthquake aerial photographs and topographic data, and we also did some field work. And based on that, we derived results regarding the geomorphology, co-seismic landslide displacements, as well as rock mass properties and the structures of the rock mass around those landslides. We then compiled all of this information into conceptual models of individual sites, and then also derived some more overarching models for failure mechanisms in these rock types. And based on that, we were also able to derive some hypotheses around initiation processes of these specific failure mechanisms. So the first site I'll be presenting is the landslide site in Turles-Greywacke. So that's the Mount Peter South site that I showed you on the map before. And as you can see in picture A here, this is a partial failure as a rock avalanche. So the upper part of the slope is an incipient failure, and the lower part of the slope has transitioned into a debris or rock avalanche. And in the incipient portion of the slope, we can detect some deformation features. And this is quite a cool opportunity that we get here, that we can actually still see how the slope deformed during the earthquake, because in many other failures, we just see the debris or rock avalanche deposits and don't actually get to see any deformation features in the slope anymore that led up to the failure. So in the upper part of this incipient part of the failure, we see translational movement. So there's a few tension cracks around there, but not that much deformation. So it's a mainly translational deformation of the upper part of the slope just below the headscarp. Then in the central part of the slope, which is indicated with the blue color in panel B there, we can see some compressional geomorphological features like counterscarps and bulging. And then in the lower part of the incipient part of the landslide, in this purple area there, there's a lot of tension cracks. So we think that this is the area where the landslide started extending and actually started sliding, and then transitioned into the debris avalanche that caused the disruption of the ground, where we can just see some debris in the landscape now. So we also carried out some digital image correlation analyses using pre and post earthquake aerial imagery. And as you can see in these figures here, the average displacement of the incipient part of the landslide is about 6.5 meters. And in the area of profile 1, the displacement magnitudes below the headscarp stay relatively constant before you get into the disrupted part with many tension cracks where we can't measure the displacement anymore. And in the area of profile 2, we get an increase and then decrease of displacement magnitudes. So that's the part of the slope that is a bit less steep and also hasn't transitioned into a debris avalanche. We also took some structural measurements in the area, and based on that, we can say that there's no large-scale persistent discontinuities that could explain failure. So, but there is a pretty dominant discontinuity set that we saw exposed in the headscarp, which dips with about 50 degrees out of the slope. So, based on that and the information we got from geophysics telling us that the landslide is relatively shallow, we derived that this failure has to be a step path failure where it starts failing along some of these meter scale discontinuities along this 50-degree dipping joint set, but then steps through any kind of other small scale discontinuities that it can find. So because there's such a because this rock mass is so closely jointed, there's no need to actually break intact rock to create a step path failure. So we call this type of failure in Turles Greywacke a joint step path failure. So we divided the failure mechanism into 3 different stages. So the incipient landslide stage is where you get the rupture initiation along these more dominant defects, and then a step path propagation of the failure surface along small-scale discontinuities. And the upper part of the slope that shows relatively little internal deformation is in this stage actively deforming, compressionally deforming the lower part of the slope. Then in the second stage, once the failure surface propagated all the way through the slope, you get extension and transition to sliding in the lower part of the slope, which then leads into the third and final stage of debris and rock avalanching. So on the other hand, landslides in neogene siltstone are quite a bit simpler and more easy to figure out. So this is the example of the Stanton River East landslide. You can see on the geomorphology map on the right-hand side here that there's some tension cracks around the headscarp, but the main landslide body actually moves as a coherent block. And that also becomes apparent in the results of the digital image correlation. So on the left-hand side, these red vectors show the coseismic landslide displacement vectors, and you can see in there that they're quite coherent. And in the profiles, you can also see that there's this big step of displacement magnitude from the between the intact ground, the headscarp, and then the landslide, but not much else going on. So if we then project the regional bedding orientation into the slope, we also see that the landslide vectors actually dip parallel to bedding. So this kind of confirms the hypothesis that this landslide moved as a planar translational rock slide following bedding. So this is a pretty traditional planar sliding along a persistent discontinuity that is described many times in the rock slide, and kind of confirms this initial finding from the literature that with persistent discontinuities, you expect structurally controlled failures. So if we bring all of these results back together, we can start thinking about what this means in terms of landslide susceptibility. So in Turles Greywacke, because we think the rupture initiates along some of these meter scale discontinuities, the orientation of these meter scale discontinuities could play a role in where these failures occur. Then, of course, slope angle and rock mass strength determine whether a slope is susceptible to failure or not. And additionally, because we think that these failures initiate from the top of the slope and are driven from the upper part of the slope, it is possible that they're disproportionately affected by processes affecting mostly the upper part of the slope, which could be amplification due to seismic shaking, which is typically much higher at the top of the slope compared to the toe of a slope. In neogene siltstone, on the other hand, the susceptibility factors are mainly related to the strength and stress conditions along those basal sliding planes that allow the landslide to occur. So that includes bedding orientation relative slope, as well as strength and stress conditions along the bedding plane. So strength of the bedding plane, as well as pore pressure along the basal sliding plane. And also fluvial incision could influence the depth of these failures, as well as influence susceptibility, because it influences whether the susceptible bedding planes are daylighting or not. And this has also been found in a few other landslides around New Zealand, where they did some regional studies on the susceptibility of landslides in neogene siltstone. So it ties in quite nicely with some of the other work that has been done. So we've written some of these findings up in a paper that is currently in review. So we also include an additional site-specific analysis in the paper. So if you're interested, once it's published, I encourage you to go check it out. Furthermore, I'm also still working on trying to validate these empirical hypotheses with some numerical modeling techniques. And we're also interested in looking into putting some numbers to the transition of the failure stages that I described for Turles Greywacke, to actually get help us to better predict the hazards that some of these Turles Greywacke slopes pose on infrastructure. And then finally, I'm also interested in looking into how these landslides evolve over multiple earthquake cycles, because New Zealand is a very tectonically active landscape. And as you've seen, some of these landslides are still incipient landslides, so they might fail in a future earthquake. So it would be really interesting to see how these landslides are going to evolve over multiple earthquake cycles, which could potentially inform future forecast models and could be useful in terms of forecasting where future landslides might occur. So I hope I convinced you that failure mechanisms matter and are interesting to study, and I'm happy to take any questions that you might have. Thank you.
Thank you very much, Ms. Singeisen, for your very interesting presentation. We now have 10 minutes for the Q&A, question and answer session. So if anyone's got any questions, can raise your hand or just turn on your microphone. Yeah, Abdul.
Yes, I have a question. Thank you very much. It was a very nice presentation. And I have a small question that for Turles Greywacke, you have used a geophysical technique to find out the depth of intact rock. Which type of technique you have used to find the depth?
Yeah.
Is it a resistivity survey or?
For the landslide that I showed you, the example of, we used electrical resistivity survey, which based on the fracture densities, you can kind of determine what the depth of the landslide is. And then in another site, we used MASW and P-wave refraction techniques, and a combination of these to kind of, determine what the depth of the landslide is.
Okay, thank you.
Yeah, I've also got a small question. I know you are hoping to use numerical methods to sort of validate your hypothesis. Do you have in mind what kind of numerical methods, or it's going to be like what kind of commercial software you'll be using?
Yeah, so well, it's still work in progress, but I've been using UDEC to simulate, to back analyze the failures. So I started with using UDEC, and now I've kind of moved to using RS2 because we're still trying to calibrate the models. So we're interested in having some results that we can then put the calibrated models back into UDEC. Because the tricky bit about the numerical modeling is the modeling the very fractured nature of the rock mass, because it needs a lot of computational power. So we're trying to simplify the model in a way that still captures the most relevant characteristics of the rock mass, which has proven to be fairly tricky, but I'm working on it.
Yeah, typically the larger the scale, the more computation. And then if you go 3D, that's even more time and energy intense. So, but good luck. Yeah, hopefully
Thanks.
You can get it worked out.
Jack, can I ask one question?
Yeah.
Yep. Thank you very much for your very interesting presentation. From your point of view, how much do you believe that the failure that you are dealing with, they are kind of progressive failure, a combination of the different factors, you know what I mean? Because it brings you to selection of your next step, which is numerical simulation. When you are dealing with a progressive failure, it limits your options for selecting appropriate numerical modeling. I mean that you might not go for a continuous based softwares like as RS2, as you said, or typically discrete element methods or something like that, like as UDEC. You might need a combination of these two to be able to progress simulation of the progressive failure. How much do you believe that you are dealing with such a problem, in your project?
You mean progressive fracture propagation?
Yeah, progressive failure, a mix of, yep.
Yeah, so because the rock mass is so heavily fractured, that's basically the reason we're looking into using discrete element modeling, because you don't actually need to create any new fractures for the failure to propagate. Yeah.
Yep, that's so good. Good luck.
I think we are at the end of our series today. So once again, on behalf of the organizing committee, I'd like to thank the ISRM for helping us in the organization of this event. I would also like to thank Dr. Salahattin Akik and Ms. Corinne Singh-Eisen for their very interesting and valuable presentations that address the two relevant topics in rock mechanics. We hope that this seminar provides you new insights and new challenges for future research, and there could be a periodic event for sharing ideas about rock mechanics and related topics. For this reason, we want to invite you for the next seminar that will be virtually hosted by our North American colleagues in May. Dr. Masoud Raju from Canada and Mr. Wan J. Monsell from the US will present their work respectively on directional and 3D confinement dependent fracturing, strength and dilation mobilization in brittle rocks, and stochastic discrete element modeling for pillar strength determination, a first step in risk-based pillar design approach. Further information about this event will be available on the ISRM newsletter and website, so keep in touch not to lose the next webinar. If you are interested in, if you're interested in participating, please contact us by email at the isrm.ym.seminar@gmail.com. So if you want to share your research, please do so. Thank you everyone for your participation, and have a wonderful and safe day.
Thank you.
I have a, Jack, I want to add that. Can you share the slides of today's presentation? Is it possible for you?
I think the presenter have their slides. Do you? So Corinne and Selahattin?
Can I answer that? The presentation will be on YouTube. So it is streaming at the moment, and you can always go back and look through the presentation.
That's great. Thank you. Thank you.
All right, thank you, everyone. That's it.
Thanks, guys.